Hey, this is Mr. Boyce, and we are actually going to make this our final video because the last few minutes are only like 4 pages. So we're going to go ahead and do 12 through 14 all together at one time. You don't have to watch the whole thing at one time. You can always pause, come back to it, whatever. But let's go ahead and get started. So, Unit 12, Acid and Bases. So this, you probably remember something like this on my board. You may have written it down as kind of a square type thing. Either way, just keep in mind that pH and pOH, this is going to be your 0 to 14 numbers. If you want to get that into a concentration, then what you need to do is use the negative log function. And a concentration to a pH or pOH is an anti-log. And I'm going to show you how to do that on screen. pH to pOH is pretty easy. That's just one plus the other is equal to 14. So that means 14 minus either one of them is going to give you that conversion. And I notice on here it doesn't have this conversion. This is also pretty important, and that is the concentration of H plus times the concentration of OH minus equals 1 times 10 to the negative 14. And as long as you have either H plus or OH minus, you can rewrite this equation to solve for one or the other. Okay, so this is the kind of thing you probably want to write on your note card. And if you made it this far, you'll probably have one, so that's great. Let's go ahead and get started. So pH scale. Now, this is, you got to remember pH and pOH are opposite of each other. So let's take this as being a pH scale. Right here, dead center is 7. Okay, and you can go from 0 to 14. And let's just say on the top here, this is pH. And for pH, below 7 is an acid, and above 7 is a base. Now for pOH, it's going to be the exact opposite. In fact, let's just go ahead and change colors. And so for pOH, it's going to be base and acid. So you either need to keep this in mind or convert your pOHs to pHs, whatever. But let's see what that means. So that means on the pH scale, so pH scale, the pH of an acidic solution is less than 7 right here. The pOH of an acidic solution, so this is pOH, that's down here, of an acidic solution is right there. And so that is going to be greater than 7. And then the pOH of a basic solution, that's going to be less than 7. So just pay careful attention. Is it pH or is it pOH? And that's how that works. Okay, characteristics. I'm going to go through this pretty quick, but these are pretty important. You should remember these. You'll probably see something like this. So a sour taste, that is going to be indicative of an acid, whereas a base will have a bitter taste to it. So kind of like soap, think sour, like lemon, like citric acid, that kind of thing. Okay, most indicators will turn red in the presence of an acid and turn blue in the presence of a base. So you may recall that from our lab. And then finally, very important, an OH anion. That tells you you have a base, and an H plus cation, in other words, starting with H plus, that's going to be your acid. This is our rarest definition. Okay, so an example of a strong acid and strong base. There are 6 strong bases and 7 strong acids. So for example, and you'll have a list of these, by the way, but so HCl and NaOH. POH. That's a strong acid and a strong base. Um, and what makes those important, we'll talk about that right down there. So in the titration, in the case of a strong acid and a strong base, we can use the formula N1V1 equals M2V2. Now, let me point out that is actually in most cases, and the ones you're going to come across, we can. And the reason for that is because most will balance 1 to 1. So therefore, if I'm trying to find the moles of the acid, if everything balances 1 to 1 in the chemical reaction, then I would also have the moles of base. So M1V1 works in that case. Okay, so a strong acid and base would disassociate completely. This is what makes them strong acids and strong bases. And what that means is for every 1 mole of HCl, which is a strong acid that is dissolved in water, I will have 1 mole of H plus, and I will have 1 mole of Cl minus ions. So following the same logic, if I had 3 moles of HCl and I dilute that into water or dissolve that into water, then I would have 3 moles of H plus and 3 moles of Cl minus because it disassociates completely. Okay. When a strong acid and a strong base react together, the products will be a salt and a water. Okay, calculating pH solutions. So I want to go from a concentration to a pH. So a concentration doesn't always have 10 to the negative. Sometimes it can be this. So we can still do that in the calculator. So negative log of my concentration, which is 1. And that actually turns out to be 0. And that is my POH because I'm using the concentration of hydroxide. And what the question wants is the pH. So be careful. This kind of thing happens all the time. Make sure you're reading them very carefully. So a 0, we can do that, 0 for the POH means that what I'm going to do is 14 minus 0 equals 14, and that is my pH. So be very careful that you're reading the question. Moving on. Okay, if the pH of a solution is 2.37, so this is an acid, what is the concentration of the hydrogen ions? Okay, so what I'm going to do is I am going to go in the calculator and I am going to hit second log, and that's going to bring up the little 10 with the chevron thing. And so that is going to, and then I'm going to put the negative pH, which is 2.37, and that is going to equal 0.00427. And to put that in a scientific notation, I'm going to go 10 to the negative 1, 2, 3. And so that is going to equal 4.27 times 10 to the negative 3. And so there's my concentration. I want concentration of hydrogen ions. I had the pH, so I don't need to do any further conversions. Okay, what is a POH with a solution of a concentration of hydroxide? Okay, so again, what I just need to do is go from a pH or POH to a concentration. So what I am going to do for this one is negative log of the concentration, which is 2.5 times 10 to the negative 7. I use second log for that. And that is going to be 6.60, which is my POH. So therefore, I'm good to go. Okay, what is the pH of a solution with a concentration of hydroxide? So now I have pH, I have concentration of hydroxide, so I'm going to need to do two different calculations here. So let's start off by converting my concentration. So negative log of my concentration, which is 0.75, is going to equal 0.1249. Now, this is my pOH because I got this from the concentration of hydroxide. So what I need to do is convert that to pH. So 14 minus my pOH, which is 0.1249, equals 13.88. So watch carefully, see if you need to do extra calculations. Okay, what is the pOH of a solution with a hydroxide concentration of 2.3 times 10 to the negative 6? Okay, so first thing I'm going to do is, well, the only thing I'm going to do because I want pOH and I already have concentration of hydroxide. So this is just simply negative log of my concentration, which is 2.3 times 10 to the negative 6. And in my calculator, that's going to be 5.64 for my pOH. Now, unlike stoichiometry, we're not going to do like dozens of these. So we just did these recently. The important thing is make sure you know how to do this in the calculator and you'll be just fine. Okay. Titration. So remember, strong acid, strong base, these disassociate completely. Both of these are going to break apart. You have H plus and Cl minus, and this is going to form an A plus and OH minus. So if I were to write this out and balance it, it would still go together 1 to 1. So I don't need to take that step. I can just do M1V1 equals M2V2. Okay, and so let's figure this out. Uh, M1 is 0.1, so let's put that in there, 0.1 times V1. Now, here's the problem with V1. Pay very close attention. This has to be in concentration and it has to be in volume, which is in liters. This is in milliliters, all right? And so I need to multiply this by 1,000 in order for this to work. So 0.054, just move that decimal place on over 3. Okay, and equals M2V2. And so in this case, my M2 is what I'm looking for. And my V2 is right here. And that is already in liters, so that's nice. 0.125. Okay, so if I want to solve for x, what I'm going to do is just divide both sides by the same thing, which is 0.125, 0.125. It cancels on this side. And so here's my equation. In a calculator, I'm just going to put 0.1 times 0.054, close those parentheses, divide that number by 0.125, and my answer will come out to 0.0432, and that's my concentration in molar. Okay, let's do one more of these. Now, what I like to do, UBU, but if this works for me, is M1. I'm still using M1V1 equals M2V2. And so let's take a look what I have. 25 milliliter solution. This is my V1. is neutralized by 37.5 milliliters. I know I'm going to need to go ahead and change that later, but let's go with that for now. And here's my M2. What is the concentration of the HI? That is going to be my my M1, and also what I'm solving for. So I want to solve for M1. So I'm going to rewrite this formula to solve for M1. So I'm going to divide by V1, divide by V1. This cancels. Oops, my bad. This cancels. And I'm left with M1 equals M2 times V2 over V1. I like to do that. Just plug them in a way that I can use to solve. And so let's put that in there. M2 right here. This is molarity, so I don't need to change that. 8 times my V2, and my V2 is right here, 37.5 milliliters. I need to convert that to liters, so 0.0375, and then divided by my V1, and my V1 is 25 milliliters. So once again, 0.025 liters. And then I can just put that in my calculator, and that's going to come out to 0.282. Yeah. Okay, so that was it for acid and base. Acid and base is very much shortened. That means there's pretty much nothing on there you can ignore. So make sure you know how to do all of these calculations. Uh, molarity, we're going to stick with the M1V1, make it a little bit easier, but make sure you know what you're doing on these. Okay, let's move on to redox. This is where we just did this. So again, on this one, we're not going to spend a whole lot of time on this one, but we do want to make sure we include this in the review. So when it comes to redox, there's a couple rules, and you want to know these rules because they're very helpful. And that is number one, three elements equal zero. So this is anything in its normal state. So anything that's on the periodic table, an individual atom, as long as it's made of one atom, is zero. And that includes things like Cl2 because that's still one type of atom. So it doesn't matter how many I have. If it's one type of atom, it's not bonded to anything else, that's going to be zero. Two, oxygen. Oxygen is your friend, and then these compounds, it's going to be a -2. Okay. Your one exception is hydrogen peroxide, but don't worry, you won't see it come up. So just trust oxygen as being -2. Three, hydrogen in a compound is going to be +1. There is an exception. And that's metal hydrides. And so that just means a metal in hydrogen, where hydrogen comes after the metal, which means it has to take the negative charge. But again, that's an exception. So you won't really see that, but make sure you know it's there. And then number four, this pretty much goes for any of your positive metals. So group one, and that's going to be, well, hydrogen is a +1 for us, so that would kind of include that. But uh, hydrogen, everything below, everything in that first row of your periodic table is going to be a +1. And this is basically the same charge that you would use for your ionic charges if you were putting it together as a compound. And group two, those are your alkali earth metals. those equal I plus 2. So when you're looking at these, you have oxygen, you have hydrogen, you have all the group 1 and 2 metals, and you have the green dots on my periodic table. Those are your set charges. Those are ones you already know. Free elements, you know those are 0. Uh, and this is very important, and I'll point this out as we're going through these, but assign oxidation numbers per atom. And let me show you what I mean by that. Okay, so first, let's take a look at what our oxidation numbers are on this one. So this is calcium. This is all by itself. So it's a 0. Uh, Beryllium here, same thing. It's diatomic, but it's still just made of beryllium, so 0. Calcium, this is your group 2, so we already know calcium's a plus 2. Now, this doesn't have a charge. I need this to be 0. Now, do not, let's put this in red. Don't do this. Don't even write this down. Don't do -2, even though that balances, because remember, this has to be per atom. So we do not want to do that. We want to put -1. I have 2 of them, so it works. It all cancels out. That's fine. Okay, so now what I want to do is see what was oxidized, what was reduced. So the calcium went from 0 for an oxidation to +2, so that definitely changed. And the beryllium went from 0 to -1. So both of my oxidation numbers changed. Now, what was oxidized and what was reduced? So a lot of people get confused, as reduced means to gain electrons. But if you think of this as a charge thing, then the charge went from 0 to -1. So this was reduced, and then oxidized means to lose electrons. And the more electrons, more negative electrons you lose, more positive you're going to get. And so the calcium is what was oxidized, which means your oxidizing agents are the opposites. Okay, for a half reaction. So I'm just going to go basically in order that it is here. So the calcium's on this side. There we go. Okay, and so for here, I've got calcium. I've got my arrow, and that is going to turn into calcium with a +2, and that means it lost 2 electrons. So here's my half reaction. Okay, for the beryllium, I had Br2, okay, and over here. Now, in this case, we want to write this as individual atoms. So this is going to be 2 Br minuses. Okay, and in order to do that, it had to gain 2 electrons. So 2 electrons. So you want to keep the electrons on opposite sides. In this case, this is balanced, so I'd be able to cancel these out if I wanted to write a net ionic equation. Okay, but let's stick with oxidation numbers. This is seriously important. So Cl2 has a 0. Hydrogen, we already know hydrogen, right? And because I know hydrogen's a positive and they're 1-to-1, then this beryllium had to be negative. Again, hydrogen is positive, and so that makes this Cl only have 1. That's going to be negative as well. Br2 out there on its lonesome, a 0. So did they change? Well, let's see. So first off, beryllium, Br, did its oxidation, or let's start with chlorine. Did its oxidation number change? Yes, it went from 0 to negative. Hydrogen, did it change? Nope. +1, +1. Okay, so therefore, let's move on and we got negative to 0. So those are our changes in oxidation numbers. So oxidized is beryllium. This is losing electrons going from a negative to a positive. Its charge is increasing. That means it's oxidized. And the charge that is reduced is chlorine. Its charge reduces. So therefore, these are your agents. And for the half reaction, I've got here, now this part, I'm writing the half reaction. The first one was already balanced. This is not balanced because I have two berylliums on this side and only one over here. So I'm going to put a 2 there. Uh, Chlorine, Cl2, I've only got one on the other side, so I need a 2 there. And doing that also balances my hydrogens. So now we have 2 of everything. This is balanced. So when I write the half reaction, I got to take that into account. So 2 Br minus, all right? So it's right there in the formula, turned into Br2, and that kind of makes more sense as to why I wrote it this way on the previous one. Plus 2 electrons. And for my reduction, I've got Cl2, right? That was right here. And that turned into 2 Cl minuses, which meant they gained negative electrons. Those had to come from somewhere, and that's where they came from. And let's take a look here. AgNO3, this one's a little bit more detailed for oxidation numbers. So silver, well, first off, we already know oxygen, -2. It doesn't matter how many I have, oxygen is just -2. Silver is a +1. You can see its charge on the periodic table. And that means that 3 times 2 is 6. So I have 6 negative charges in the oxygen. One of those charges is canceled out by the silver. So I have 5 remaining. I have only 1 nitrogen. So this is going to have to be a +5 in order to balance that out. Copper Cu all by its lonesome. Now, in this case, copper is now that it's in a compound, I can trust it because it's a +2 because it's an alkali earth metal. So there you go, +2. Oxygen, -2. And in this case, I have 3 times 2. So I have 6 oxygens. Each one's a -2 charge. That's 12 negative charges. I have 2 positive charges, so I have 10 negative charges altogether. But I have 2 nitrogens, so I can split the difference and put a +5 for each nitrogen. Remember, the oxidation number is per atom and not the overall charge we're needing to accomplish. Okay, so Ag all by its lonesome, it gets a 0. And so now I can compare here. And first off, the silver, did it change? Yes, it did. The nitrogen, did it change? No, it did not. So I'm not concerned about it. The oxygen, did it change? Nope. -2 to -2. And this copper, did it change? Yes, it did. 0 to +2. So those are the ones I'm going to focus in on, especially if you're writing half reactions. So oxidized, the copper went from 0 to +2. Its charge increased. That's oxidation. So that's Cu. And then my silver went from +1 to 0. Its charge reduced because it gained electrons. And so that's going to make this my agent. Sorry, +1. There we go. Okay, the half reactions for this kind of dropped off the sheet, so that's fine. If you're at all stuck on this, just go back and kind of look at this unit. The important thing, assigning oxidation numbers and identifying what was oxidized and what was reduced. Believe it or not, that's it for that unit. That's why we're doing 3 at one time, just kind of get this done. So nuclear, this is the most recent. We just finished this one. So hopefully this is still kind of in your head. Well, let's just finish this out. So explain the difference between fission and fusion. So fission. So fission, a nucleus splits and that releases neutrons, causing a chain reaction. So nucleus. So the split's important. It splits into two different things. And when it does that, it releases neutrons, and those neutrons will hit other nucleuses and cause a chain reaction. Okay, and this picture on the bottom, this is an example of that. So I have a nucleus and it strikes a large radioactive unstable element, makes it more unstable, and then it splits right here into two. And when that happens, it releases a whole bunch of energy and some extra neutrons. And those neutrons are going to go on to basically do the same thing to another isotope. And so there's your chain reaction. Okay. Fusion. This is much more powerful of one. So fusion, what happens is nuclei uh, combine or fuse together. And this is basically what's powering the sun is you have lighter elements, protons combining to form heavier elements. Okay, so alpha, beta, and gamma decay. Let's start with alpha. Now you need to be able to recognize these. So let's look at 240 over 94. 94 protons means plutonium. Remember, the 240 is the sum of the protons and the neutrons. So if I wanted to know how many neutrons there were, I would just subtract 94 from 240. But what I want to do is show alpha decay. And alpha decay is two protons and two neutrons. So if I lose that, my mass number, or sorry, my yeah, mass number is going to drop to 236. It's going to drop by 4. And my atomic number is going to drop to 92. That's going to drop by 2 because the atomic number is protons only. And it's going to become uranium and then plus 4 over 4 to helium. And that is because I have two protons, and this number is protons plus neutrons. So two protons, two neutrons, the total being 4, two of which are protons. And let's see, beta. And beta kind of looks like this goofy bee that comes out the bottom here. And so let's take a look at an example of 14 over 6 carbon. So this would be carbon with 6 protons, which is what defines carbon as carbon. And the 14 is the sum of the protons and neutrons. And most carbon is carbon 12. There's a little carbon 13. Carbon 14 would be a bit unstable. And so what would happen in this case is a proton is basically just a neutron is a proton and an electron together. So if that splits off, then what's going to happen is something pretty interesting here. I'm going to end up keeping the same mass number because the number of protons and neutrons are still the same, but one of those neutrons turned into a proton. And so this now becomes nitrogen. So my atomic number goes up because I have one more proton, but my mass number doesn't change at all because I still have the same sum of protons and neutrons. And then also I'm going to have an electron, which in nuclear chemistry is generally written like this. Okay, so remember a neutron is a proton plus an electron. And so if it splits off, You're going to keep the same mass number, but you are going to go up. Well, you're going to go up one proton. Okay, I don't have space to show gamma, so let's just answer this very easy question right here. Which particle has the lightest mass? So if we're talking about alpha, beta, and gamma, alpha is really big. It's two protons and two neutrons, so 4 AMU altogether. That's pretty big. So alpha is the alpha. It is the biggest. Beta is just an electron that's being put out. And so that's quite a bit smaller. And then gamma, that's just pure energy. That's really small. So let's take a look at a gamma. I'm just going to use this space over here for gamma. Okay, and gamma, you can draw that as it's kind of a squiggly looking Y. I'm not very artistic, but there you go. So 230 over 90. Okay. And so this is a very large radioactive isotope, and this is going to start off, we're going to do an alpha decay. So I'm going to take out two protons and two neutrons, which is going to drop my mass number to 226. So that's a deduction of 4. And my atomic number is going to drop by 2. So 88. And 88 is radon. So Rm. So plus an alpha particle, which is a 4-2 helium. And then in addition, we are releasing energy in the form of gamma radiation. So gamma radiation has no charge and no mass. It's just pure energy. Okay, last question, and then we are done with our entire review. How cool is that? So I've got, I want to label the points from left to right in this below illustration. So first one, resulting radioactive daughter nuclei. Okay, well, uh, I've got right here. Oops. This is number one. So after the split, I have two daughter nuclei right there. You want to call them that. And so 1 and 2. So there you go. Resulting radioactive nuclei. That's this box right here. Okay. Number 2, right? Neutron being used to bombard the radioactive isotope. And that one, that's right here. This is the neutron being used to bombard that isotope. Number 3, the nucleus splitting. Okay, so 3, that's right here. That's what's happening. The nucleus is splitting. Number 4, neutrons being released after the nucleus splits. There we go. Right here, all of these. That box could have been on any one of the 3. And then finally, number 5, radioactive isotope before splitting. And that's right there. Okay, I believe that is it. So just be very careful. Make sure that you know what the different symbols here mean. You have your alpha, you have your beta. Make sure you know what's happening with the mass number and the atomic number and why. Make sure you know why this atomic number went up, but the mass number didn't. All of that is very important. Make sure you do know the relative sizes and you should be good to go. So, all right, if you have any questions, just let me know and I will see you in class.